so thank you to Seth, Christian, and Justin for putting this together. This is wonderful to do a talk remotely and still be able to reach people during this uncertain time. So what I'm going to talk about today is breaking graph symmetry. Okay, so what we're going to be doing is starting with graphs that have some degree of symmetry, and then we're going to see how we can remove them. Okay? So for example here, if I start off here with a path and then a cycle, we'll see the path there has some symmetry, right? We've got rotations, or in this case here, well, reflections here. With the cycle, we can also reflect it, but then we could also spin it, right? We got rotations and reflections. And then for another graph, we've got another graph here that has lots of symmetries in it. Okay, so where we begin here is with what do we mean by removing symmetry, okay? What we hope to end up with here is a graph with no symmetries at all. So we'll see here, this is a picture of a graph that's known as asymmetric, okay? And we can see here, what we can do there is sort of put sort of a labeling on the vertices of the graph, or we can make some modifications to the graph and end up with something that's asymmetric. So with this graph here, this graph is definitely asymmetric here, and we can see the labeling. Each vertex is in some ways, sometimes distinguishing, right? It sort of is different from all the other vertices. The red vertex is the only vertex of degree 1 that's adjacent to a vertex of degree 3. Orange is the only vertex that's adjacent to vertices of degree 1, 2, and 3. Yellow is the only vertex that's adjacent to vertices of degree 3, and so forth. We can see each vertex has a unique property that the other vertices don't. Now, asymmetric graphs seem to come up here with, were first made very popular by Erdős and many back in 1963. And in terms from an algebraic point of view, each graphs whose automorphism group is in fact trivial. Okay, they also listed the graph we just looked at was known as this is the smallest asymmetric graph. Okay, so all graphs with 5 or fewer vertices are not going to have this property. We also have the smallest asymmetric tree. We've got a vertex of degree 3, and stemming from that is a path of length 1, a path of length 2, and a path of length 3. This graph is asymmetric. Now, what do we mean by if a graph is non-asymmetric? Okay, so I've got the double negative in there, okay? It's tempting to say, well, why don't we just call it symmetric? Okay, but it turned out, and that's in fact what Erdős and Renyi did back in 1963. But since then, there's been a lot of works on what are known as symmetric graphs, where they're defined to be graphs that are edge transitive or vertex transitive. And what that means is that graphs where edges could be interchanged with each other. So for a graph is edge transitive if for any two edges, E1 and E2, G minus E1 is isomorphic to G minus E2, and that's true for any pair of different edges. Okay, so Albertson and Collins defined what was known as the distinguishing number of a graph. Okay, so this is where you're putting a labeling of the vertices with R colors so that no non-trivial automorphism preserves all of the vertex labels. So here's what they did here. Okay. So we'll see here, if we look closely, stemming from the start here, we've got sort of the binary combinations plus 1, right? 1, 1, 1, 2, 2, 1, and 2, 2. And that makes that graph sort of distinguishable there. Now, undergraduate REU students and I, okay, a couple of years ago, defined what we called the asymmetric index of a graph. That means we're going to start with a graph that is non-asymmetric, and then we're going to add or remove edges, and we're going to end up with a result with a graph that is asymmetric. Okay, so here's our graph here. I've added in 2 edges, and now this graph, the resulting graph, is asymmetric. So we say this graph has an asymmetric index of 2. Okay, so here's the question. Which method is more efficient for removing symmetry from graphs? Okay. Well, as you can imagine here, it depends. So where we can begin here is if I look at this same graph we had earlier, we saw that we can use two different types of labels and have this resulting graph here, the resulting labeling there is asymmetric. Okay. Now, we can actually extend that. So if I extend the number of pendant paths there from 4 to 8, it allows me to go longer, okay? And I can still get by with just using two different labels, okay? So I can say that the distinguishing number of this graph here, 8 spokes, each of the spokes has length 3, we get a distinguishing number of 2. And we can continue this as far as we like, right? We make more and more paths can be added in here, provided we make them longer so that we have used up, so that we can take advantage of all of the different combinations. Okay, now when it comes to the asymmetric index, okay, we have to do a fair amount of work here. In this graph here, we have to throw in 4 different edges here. Okay? Turns out that the asymmetric index is going to be at least half the number of pendant paths. And what we want to avoid here, we want to throw in enough edges. That's being used to distinguish these pendant paths from each other. We don't want to be left with 2 pendant paths that are not attached to any edges whatsoever. Okay, so what you find here is that the asymmetric index of this graph is in fact 4. Okay, so what we have here is a family of graphs where the asymmetric index minus the distinguishing number is going to be arbitrarily large. And we can do that by putting lots of these pendant paths and then making the length even longer. Okay, so now if I flip this around a little bit, if we look at graphs where the distinguishing number is high, okay, so for distinguishing number of K7, okay, every vertex has to have a different label here. Okay, so it turns out here the distinguishing number of K7 here is very simply just 7. Okay, this was one of the elementary results from Albers and Collins. So we can extend that there. The distinguishing number of Kn is n. Now, for the asymmetric index of K7, okay, seems like we have to do a lot of edge removal, removing a lot of edges to get this graph to result in an asymmetric graph. So what we can do here is sort of flip this around. We said we could either remove edges from a graph or we could add them. So instead of starting with the complete graph, we can start with the empty graph or discrete graph and now add in edges so that the resulting graph is asymmetric. And we can do that pretty easily here by adding that smallest asymmetric tree with 6 edges. Okay? So what we get from this here is that the asymmetric index of K7 here is 6. Okay, which is less than the distinguishing number. So we're seeing that we've got a case here where the asymmetric index is less than the distinguishing number. Okay, so what we can do there, if we want to expand this a little bit, thinking about the number of edges in an asymmetric forest on n vertices. So if I've got K43 here, I can add in or remove 37 edges to make the graph asymmetric. So this is what it looks like. So I've got starting off with 43 isolated vertices. I can now put in an asymmetric forest. And what I mean by that is I've got asymmetric trees that I'm putting in, and all of those asymmetric trees are mutually non-isomorphic. So that's going to end up with a graph that's asymmetric. Okay, it turns out that roughly this would get this something like the asymmetric index of Kn is about 6n over 7, roughly. Turned out as we were writing this up here, we actually found a paper by Luis Quintos back from over 50 years ago, where basically he looked at creating asymmetric graphs and asymmetric forests, and that would actually give the same result that we have that I'm presenting here. Okay, so with complete graphs, there we have a case where the distinguishing number minus the asymmetric index is arbitrarily large. Okay, so we started looking at graphs that have where the asymmetric index is 1 and the distinguishing number is 2. And if I just took that first asymmetric graph and I put in the edge, so that's what I'm going to start with. If I remove it and have an asymmetric graph, I can look from the labeling perspective with an asymmetric graph, label everything 1. And then for the removed edge, we can put in 2s for those vertices that are incident to that removed edge. So we also looked at something called minimally non-asymmetric graphs. And that's where the removal of any edge results in an asymmetric graph. Okay, and here's a collection of these for a small number of vertices here. There's actually an infinite number of these. In fact, we can, and of course, the distinguishing number of these is going to be 2. We can actually extend some of these to an infinite family pretty easily. And again, these are graphs here where the removal of any edge gives us an asymmetric graph. Okay, so here's the question here, right? What is the distinguishing number for the following graphs? So this is the Doyle graph. It's vertex transitive, and we can see there it's a beautiful shape there, but it's got a lot of symmetries in it. Okay, so the question is, how many labels do we have to use? How many different types of labels do we have to use to distinguish all the vertices in the graph here? So it turns out that we can actually just get by with 2, which is surprising. Okay. So the complete graph, right, we had to put in a different color for every vertex. But here, we can get by with 2. And here's why. The Doyle graph has a very nice property here. It turns out that it's minimally non-asymmetric. So if I remove any edge, let's say I remove the top edge here, what we do there is we can replace the vertices that are incident to the removed edge, we give a color of 2, and all the other vertices get a label of 1. And what that gives us is that the distinguishing labeling with only 2 colors. Okay, another example of a graph with this property, the Bauer graph. The Bauer graphs where the first index there is 2 will meet this, this property here, at least for the small ones that we've looked at. So the distinguishing number here is 2. And again, with these minimally non-asymmetric graphs, we can actually label any pair of vertices with 2, and then all the other vertices in the graph with 1. Okay, so with some open problems here, okay? When we deal with disjoint unions, this is actually a big challenge. Okay? For the distinguishing number, it's actually not that bad. So this result, I'm pretty sure it's known. It's very, very, very easy to do. If you've got disjoint copies of the same graph and you take their union, so let's say we start with complete graphs, it's just very simply a nice formula there. You start off in the first graph by labeling all the vertices different, and then you only have to change one vertex in the next graph, and then you can keep doing that as you move from right to left there. The reason why this works, of course, is that in the middle graph there, all those vertices are adjacent to a white vertex, but that's not true for any of the vertices in the graph there, in the other copies of the graph. Okay, but here's where we run into a bit of trouble here. When we look at the asymmetric indexes of disjoint copies of graphs, we don't know very much at all. Okay? In fact, even for, let's say, the disjoint union of complete graphs, we don't know too much. Now, it's tempting to say, well, what we could do is start removing asymmetric trees from these different graphs. And as long as these asymmetric trees we're removing, right, are non-isomorphic, mutually non-isomorphic, then we can actually end up with a set of graphs that's all the resulting graph is going to be asymmetric. Okay, so that will work, but it only gives a bound. And the key there is that we don't know too much about adding edges, because we're allowed to add edges in to create asymmetry as well. Okay, so from the removing standpoint, what I described there is probably the best approach, but with the asymmetric index, you might be able to add edges selectively and then come up with an asymmetric graph. Okay, so I think I will end there. So I'll thank you again for this presentation, and thanks also to Brendan Rooney here, who's been working with me on this project.
Okay, thank you.
If you have the right number of copies of that graph, is it possible to add edges to turn each one of those graphs into a vertex in an asymmetric tree.
So
So let's suppose that you are taking 7 copies of K7. And then you make that asymmetric tree that you had shown a couple times, where each vertex is now a copy of that graph.
Is that almost like a Cartesian product type of thing?
I'm not sure.
Okay.
I mean, you were talking about you weren't sure about adding edges, so I thought maybe this would be a way to.
What are you thinking, like a single edge between like complete graphs?
No, but not a single edge, because if a single edge between each one, it would be, you'd still have symmetries on each one.
Sure.
So maybe putting some K77 going from one side to the other side. But of course, it increases the numbers pretty high. I just didn't know how high it would increase.